Uh, we can have our next speakers. Ghadem Safaei from ISPS. He's going to talk about star clusters with top-heavy IMF. Ghadem, are you
Hello?
ready?
Yeah, can you hear
Okay,
me?
yes, we have your voice. Go ahead, please.
Hello everyone, good afternoon. First, I want to appreciate scientific and organizing committee for giving me this opportunity to have a talk in this virtual meeting. I'm going to present the results of a large grid of embodied simulations for a study on the top-heavy IMF as the initial conditions of star clusters. The first, an overview. The IMF describes the Beers distribution mass of stars. Krupa in 2001 for the first time introduced the canonical IMF as the initial parameter for star clusters. Without considering the residual gas expulsion, Baumgart-Machino in 2003 showed that the lifetime of star clusters is scaled with relaxation time. In this work, we calculate a grid of models over a wide range of stellar mass to study on the effect of top-heavy IMF. The outline of this talk is a short introduction, then I will talk about the evidences for top-heavy IMF. Finally, the result of our simulations will be presented. As the motivations, we want to answer these questions about the high dissolution rate of star clusters, relation of dissolution time and initial mass and alpha 3, and the astrophysical parameters of star clusters over the evolution time. I have very short introduction, just I will talk about the star cluster and top-heavy IMF. In this schematic figure, I want to describe that star clusters form from giant molecular clouds. Bound embedded star clusters form readily here and survive until the dissolution time despite additional mass loss process. Here you can see different internal and external effects cause two star clusters lose their mass and then dissolve. For example, the tidal field, two-body relaxation, stellar evolution are some of them. At the left side, you can see a typical cluster at the burst time, and at the right side, you can see a star cluster near the dissolution time. We have two main evidence for top-heavy IMF. The first, UCDs, and the second, the globular clusters that form in dense and metal-poor environment. Ultra-compact dwarf galaxies are more massive than globular clusters, and the value for the alpha-3 observation and theoretical study for them is lower than the canonical value. As you can see in this plot, it's lower than it's predicted for canonical value. Open circles here you can see is in this plot show the value of alpha 3 for globular clusters. The solid line shows the value for alpha 3 as a function of the initial mass of cloud from these equations. The alpha 3 for metal poor globular clusters, as you can see in here, here these open circles are lower than the canonical value for metal-poor global clusters. We performed simulations with different initial clusters. Mass ranges in the range of 10 to 4 to 10 to 5. All clusters move on circular orbit with circular velocity 220 km per second at galactocentric distance 8.5 kiloparsec. Cluster forms in metal-poor environment. We have tidal field effect and gas expulsion effect. For the initial size of our models, we use Marsh-Krupa relations. Therefore, initial size of our models in the range of 0.33 to 0.45. As you can see, the size of our clusters is very small and it takes time to simulate the models. We use IMF in the form of the three-segment power law as follows. In order to cover the top-heavy model and canonical model, alpha 3 is varied from 1.3 to 2.3, 1.5 to 2.3. In this table, vertical column shows the initial mass of models. You can see the alpha 3 here, and here is the initial number of our models. For this model, with initial number nearly 4,000 particles, it takes 1 day to dissolve this cluster, and for this model, it takes 190 days. We have plotted the mass of a cluster divided to the initial mass as a function of time. For our models, we have 3 main mass loss paths. The first within just few megayears from here to here. The mass loss is dominated by gas expulsion and stellar evolution. Second phase is dominated by two-body relaxation. And the third phase is dominated by the tidal field. At the first few megahertz, the size of star clusters expand strongly and reach to higher value and then decrease until the dissolution time. The tidal radius that is plotted by dashed line decrease continuously. In this plot, we can see dissolution time for more top-heavy model is faster than the canonical models. The top-heavy models is plotted by yellow, and the canonical model is plotted by red. And horizontal dashed line shows 12 gigahertz, and dashed dot line is the result of Baumgart-Martino 2003. In this plot, not only we can find the linear fit for each family of model, but also we can find the minimum survived mass for each models. The figure shows the minimum survived mass of different alpha 3. For top-heavy models, the dissolution time is shorter than models with canonical IMF. Therefore, the minimum survived mass for top-heavy models is higher than the canonical models. In this figure, you can see the expansion factor that is defined as the ratio of the maximum value for the half-mass radius divided to the initial value, and we find a linear fit for these figures. The mass density profile for all models are the same at the burst time, and after just 10 megahertz, you can see the mass density profile for canonical models is higher than the top-heavy models. The mass-to-large ratio in visual band is higher for canonical models than top-heavy models. Also, by changing the upper stellar mass limit in IMF from 100 solar mass to 150 solar mass, we will have the dissolution faster for models with 150 than other models. Also, our models has stellar evolution. This will cause our model dissolve faster than the single mass models. In the earlier stage of the cluster evolution, the number of dark rim bands, including white dwarfs, neutron stars, black holes, increase as the stars evolve. These stars are most massive than, and therefore least likely to escape. For globular clusters near the end of their life, most of the cluster mass should be in the form of compact rim bands. Here you can see the number of white dwarfs. Number of white dwarfs for canonical models is higher than top-heavy models. Also here you can see the number of neutron stars. The number of neutron stars for top-heavy models is higher. The number of black holes for top-heavy models is higher than the canonical models. Here you can see the number of neutron stars, and the number of neutron stars also for canonical model is higher than the top-heavy models. For more detail, you can see the number of neutron stars and number of black holes within 100 megayears and 120 megayears. One of the most important parameters that we can compare with observation is core radius. In left panels, we plotted the core radius, also the central concentration parameters of star clusters is plotted in right panels. You can see the central concentration for canonical models is higher than the top-heavy models for all of these panels. The red one is higher than the yellow one. Also, the mass function as a function of the stellar evolution is changing. This will cause the slope of mass function will change, and by linear feed we can find the slope of mass functions. In this plot, we plotted mass function slope for mass in the range of 0.3 to 0.8 solar mass in main sequence stars, and plotted against central concentration. The left panel shows the 100 megahertz, the next panel 500 megahertz, and the right panel shows 10 gigahertz. The linear red line shows the Marchi et al. 2007 results, and black field circles in here shows the results et al. 2010, sorry. And each of these symbols shows one simulations. As you can see, the slope of mass function decrease as a function of time. Also here we plotted the slope of mass function as a function of the relaxation time. And summary, by increasing alpha 3, we can see the dissolution time will increase for constant initial mass. The gas expulsion is dominant at the first sphere megahertz. The dissolution time for constant alpha 3 will increase by increasing the initial mass cluster. Also, mass to light ratio for canonical model is higher than the top heavy models. The expansion factor is changing from 15 to 30 from different models, and we found a linear fit for that. Within the Hubble time, the cluster with top-heavy IMF, these are faster, and also the stellar evolution will cause the cluster evolve faster. Also, our grid are useful for other models for checking the March-Grupa relation. Also, March-Grupa 2000 12 relation for alpha 3 as a function of the metallicity. Thank you for your attention. I'm ready for your question.
Okay.